Okay, so page 174, we're giving this one, which is a chemical reaction to make water. So, you can think of this like a recipe, like we were talking on a remote session on Monday. We were talking about making sandwiches. We were talking about that little simple recipe to make cheese sandwiches. This is a recipe to make water from hydrogen and oxygen. And there's a ratio here. The ratio is 2 to 1 to 2. And so just like when you're making cookies or something or any other recipe, if you want to double the cookie recipe, it works just fine as long as you double every single ingredient. Or you could cut the cookie recipe in half and cut every ingredient in half. And this is what we're talking about here. The most important thing to remember is that this ratio only works if you're talking about numbers of things, kind of like we talked about with the sandwiches. So in other words, I could interpret it as 2 molecules of hydrogen will react with 1 molecule of oxygen to make 2 molecules of H2O. I could interpret it that way. Or I could interpret it in terms of moles. 2 moles will react with 1 mole to make 2 moles because moles is a number of things, just like dozens. What does not work is masses. It's not true that 2 grams of hydrogen would react with 1 gram of oxygen. And so that's kind of the whole conflict of stoichiometry, because grams is the thing that we can measure. You can't measure moles. But anyway, we'll get to that. Let's start with just letter A. So it says how many moles of oxygen. So again, we're trying to find the equation is balanced, so step 1 is taken care of. Step 2 seems to be skipped. Identify what you're trying to find in the required unit. We are trying to find moles of oxygen. What are we being given? 2 moles of hydrogen. So looking at our map here, we are being given a number of moles, and we are asked to find a number of moles. And we're just going to utilize the mole ratio. That's all we're going to do here, and this is going to take 1 step. So it's literally this. The ratio is 2 to 1. The problem says you got 2 moles of hydrogen. 2 moles of hydrogen react with 1 mole of oxygen. The answer is 1. Because that's the ratio. It's a 2 to 1 ratio. So if I have 2 moles of hydrogen, I'm always going to have half as many moles of oxygen. If we look at B, how many moles of oxygen? So again, we want to know moles of oxygen, but this time it says 4 moles of hydrogen. So if 2 moles of hydrogen react with 1 mole of oxygen, 4 moles of hydrogen would react. How many moles of oxygen would that be? 2. That's correct. It's 2. It's half as many because it's a 2 to 1 ratio. So on these problems like these where it's just moles to moles, all I'm thinking about is the ratio and keeping it in the right proportion. Let's look at another one. How many moles of water, so again, we're wanting to know moles of water, are produced from 100 moles of hydrogen? Okay, so once again, this is a mole-to-mole problem. But this time, though, it's asking me to compare hydrogen and water. The ratio is 2 to 2. So if the hydrogen is 2, the water's 2. If the hydrogen is 100, what's my water here? Also 100, the same. Questions about any of those so far? Let's take a look at D. So D says how many moles of water are produced from 64 moles of oxygen. So again, we want to know moles of H2O, and it says we have 64 moles of oxygen. So maybe some of us already realize that what you need to do is you need to multiply this by 2. The answer is 128 because the ratio is 1 to 2. So if I have 64 moles of oxygen, I'm going to have twice that many. But what I want to show you is how we might solve this problem by dimensional analysis, because that's how I'm going to work the problems for the most part. As I've said before, I'm not going to force you to do dimensional analysis, but it has some advantages. So this is how we would do it. When we're doing this part right here, okay, we're in this middle mole ratio part. Coefficients, remember, those are the big numbers in front. If there's no number, it's the same as 1. You're simply going to set those two things equal. Whatever two things you're talking about, you're going to set them equal to each other. And what I mean by that in this case is the coefficients in this say that there is 1 mole of oxygen for every 2 moles of H2O. So I'm just using those coefficients in the balance equation to make a true statement, which is that for every 1 mole of oxygen, there is always going to be 2 moles of water. When we're doing dimensional analysis with stoichiometry, it is really important that you attach the thing that you're talking about to the mole unit, like I've done here. Because here's what we're going to do. Remember the rules for dimensional analysis. We start with what the problem gives us, which in this case was 64 moles of oxygen. I have my conversion factor here. The rule is what goes up must come down. So they're always going to alternate on different top and bottom of the train tracks. I have moles. The unit is both moles. That's why you need to attach the thing you're talking about to it. Since moles oxygen is on the top, then mole of oxygen is going to go on the bottom in the next one. And so it's 64 times 2 divided by 1, it's 128. Now, as I said, a lot of us may have been able to just figure that out without doing all this. There's a few advantages to the dimensional analysis. Sometimes the ratios are a little bit trickier. Maybe you got a 3 to 2, maybe you got a 5 to 7, maybe you got some trickier ratios that are harder to see. Sometimes people will mix it up. They'll divide by 2 here instead of multiplying by 2. If we're solid under dimensional analysis, we won't make that mistake. It flows nicely when you're doing dimensional analysis on the other parts, as we'll see. So again, I'm not saying you have to do dimensional analysis, but this is how you would do it in this case. Questions about that? So if we're not paying too good of attention and we just glance at E, we might think it's the same problem. But there is something different about it. What's the difference between D and E? Grams. Now that makes a big difference. Okay, because that ratio does not work for grams. So unfortunately, I can't just multiply this number by 2 and get 128 grams. It's not correct. If we look up at my map here, this is why we have to pay so much attention to what unit we're being given. So I am being given a mass in grams, so I'm here. So I'm going to use the molar mass of that thing. Pay attention to this too. I'm going to use the molar mass of that thing. I'm going to be dividing. Now in the context of dimensional analysis, that means the molar mass is going to be on the bottom. Okay, that's what division is. So I'm going to start with the mass of the thing I'm being given. I'm going to use that thing's molar mass to change it to moles like we've done many times before. In fact, really the only thing that we're doing new today is this middle part. I'm going to change grams to moles like we've done a million times before, and then I can use that ratio. So for example, 64 grams. So remember, this is oxygen. This is grams of oxygen. I'm going to look at the periodic table, and I'm going to make a conversion factor. I'm going to look at oxygen. Here, this is a different part here. 1 mole oxygen equals 32 grams. So I make my conversion factor there. What goes up must come down, meaning gram on top. So it should be in the bottom in the next one. And again, the map I showed up above tells me I should be dividing here. That's why the 32 is in the bottom. So 64 divided by 32 is 2. So I've changed those grams to moles so that I can access this ratio. I can access my recipe from the chemical equation. So I already wrote it down. I already wrote the answer, but another thing I was going to say is so important to pay attention as you work your way through the process. Not only what unit are you in, but what substance are you talking about right now. So we're still talking about oxygen. We had 64 grams. We changed it to moles and moles of oxygen. The next step would be to use these coefficients. This is the only time we're using the coefficients in this middle part right here. I already wrote the conversion factor up above. There's 1 mole of oxygen for every 2 moles of H2O. So the answer is 4. So by changing that unit, instead of the answer being 128, now the answer is 4. So obviously makes a big difference. Now, Jeremy Lewis in 1995, which is, if you can imagine, was when I learned how to do these problems, ancient history. I would not have done this, but I would have said to myself, oh, I know what I need to do. I need to do 64 divided by 32, which is going to equal 2, and then I need to multiply that by 2 because of the ratio. And, you know, if that makes sense to you, like, I'm totally fine with doing it that way. I do need to see some kind of work shown, either dimensional analysis or this. If you don't show your work, the reason you have to do it is because I can give you partial credit if you go somewhere wrong along the way. And also, it's definitely possible to accidentally get stoichiometry problems correct, and by making a few different mistakes that kind of cancel out. So that proves that you're not doing that. Anyway, so F, again, seems similar at first glance, but F says how many grams of water are produced from 64 grams of oxygen. So this problem is this is the classic stoichiometry problem, which is where you're going from grams to grams. So we're doing this whole thing. We're being given a mass in grams of something. We're going to change that to moles. We're going to think about the mole ratio and go to moles of the other thing, and then use the molar mass of that thing. So this is 3 or 4 steps, depending how you want to look at it. I guess I would call it 3. So we're going all the way across here. Now, in this particular case, notice the information given to start was the same, 64 grams of oxygen. So I do not need to repeat all of these steps again. I've basically already here, right? Because the starting information was the same. So in this case, I can just kind of take this stuff from above and just continue and just do one more step. And again, that works in this particular case because the starting piece of information was 64 grams in both cases. So all I need to do now is, again, a mole conversion like we've done a million of. We're going from moles to grams. So I look at the periodic table, and I go 1 mole of H2O equals 18.02 grams. What goes up must come down, so meaning mole H2O is on the top. It needs to be on the bottom in the next one. Or another way to figure out that this needs to be on top is my multiplying symbol here. But anyway, it's 4 times 18.02. It's about 72.1. I want you to notice a couple of things. Notice that I still put a 1 here. Okay, because this is the true fact. 1 mole of H2O is 18.02 grams. That's what's true. You have to use true facts. Like, I wouldn't want to put a 2 here because 2 moles is not 18 grams. That's not true. The reason I'm saying that is sometimes people will, they'll see this 2 and they'll want to put a 2 like down here, but don't do that. The only time you're using those coefficients is in this middle section. In both of these other spots, it's always 1 mole that you're working with. 1 mole equals that mass. So the only time we're using the coefficients is in that middle section right there. Questions about that? Okay, so G. Here we have, again, G is where we're at. Again, I would call this the classic gram-to-gram stoichiometry problem. It's saying how many grams of water can be produced from 56.76 grams of hydrogen. Okay, so going from grams to grams, this is going to take 3 steps. I got to turn the gram to moles of hydrogen so that I can use the ratio. I got to think about what the mole ratio is between hydrogen and oxygen, using the coefficients, and then I'm going to change it back to a mass again. Okay, so 56.76 grams of hydrogen. I look at the periodic table, I look at hydrogen, I just do H2, and it is 2.02 grams is the mass of 1 mole of hydrogen. 56.76, and you can do this, and we will start to do it soon in just one big dimensional analysis chain. That's how we're going to start doing it pretty soon, but for now we'll break it down step by step. 56.76 divided by 2.02 is 28.09. What unit is this right now? This is something that this is how we get into trouble with stoichiometry, is if we don't know what unit we're in. I was in grams, but I've just changed it to moles. This is moles. Moles of what? Is this moles of hydrogen, water, something else? Hydrogen. Yeah, this is moles of hydrogen. I started out with a mass of hydrogen, and now I've converted it to a moles of hydrogen. I've done this. The mass that I was given, now it's the moles of that thing that I was given, so it's moles of hydrogen. So the next thing we want to think about is the mole ratio. This is the only time I'm paying attention to these coefficients here. It's 2 to 2. What that means is that it's the same. It's also 28.2 moles of H2. Now, the dimensional analysis, this may seem crazy to some of you, but it would look like this. Now, when you multiply something by 2 over 2, or multiply by 2 and then divide by 2, it doesn't change it. But that's what the dimensional analysis would look like. And we need to have some kind of way of proving or indicating that we actually considered the mole ratio. And you can just like get lucky, because people sometimes forget about the mole ratio completely, and sometimes they'll get lucky and get the problem right. This proves our unit too. It proves that we're now in the moles of H2O. Now we're going to use the molar mass of the unknown, of the thing we were trying to find. So, and do that mole to gram conversion. 1 mole of water is 18.02 grams. Go ahead, Carlos.
Why didn't you multiply the 28.09 by 2?
I did multiply it by 2, but then I divided it by 2. And so
okay.
it's back to 28.09. So we're going to get about 506 grams of water. Questions about that? Yeah.
For E, how is it, like, why is it 4 and not 2? Well, because, like, we got 2 for the first one, and then we did it again and got 4.
Yeah, so what he says is, it says how many moles of water are produced from 64 grams of oxygen. So what I did here is I changed the moles. So we had 2 moles of oxygen, right? But what the equation tells me is that for every 1 mole of oxygen, I'm going to have to use 2 moles of hydrogen. So if I have 2 moles of oxygen, I'm going to have to use 4. So the question was asking about oxygen. It's just like I was saying, with the sandwiches and the cheese the other day. If you use 1 slice of cheese, you're going to have to use 2 slices of bread. If you use 2 slices of cheese, you're going to have to use 4, and so on. So it's just the ratio between oxygen and hydrogen is why that happens. Okay. Appreciate the questions. Any other questions? So if we then go down, I'm going to just try to copy this whole thing. If we go down to number 2, it's a new series, like this, except it's got a new reaction here. And it is N2 plus 3H2 yields 2NH3. This is arguably the most important chemical reaction in the world and one of the most commonly produced chemicals. That NH3 is ammonia. This is how we produce all the fertilizer that we do. And if we did not have this reaction to produce all this fertilizer, we simply could not feed the population of the world like we have now. People would be starving to death all over the place. So very, very important chemical reaction in this one. And, there are plenty of factories that their job all day long is to make ammonia, NH3. So, like this question says, how many grams of nitrogen react with 34.54 grams of hydrogen? Okay, so question mark grams nitrogen, 34.54 grams of the H2. Now, don't get too wrapped up, and some people get a little confused or something, like when it says react with, or like the question below says required to produce, and so on. That type of language, that doesn't change anything about how you do the problem. It's just saying react with because nitrogen is another one of the reactants. I can use this same process and this information. I could either figure out the grams of NH3 that I'm going to make, or I could figure out the grams of nitrogen that's going to react. The process would be exactly the same. So that language doesn't really change how you approach the problem. But this is going to be a 3-step process. There's a ratio here. It's a 1 to 3 to 2 ratio, but it's a mole ratio. It's not a mass ratio. So I'm going to have to change this grams to moles, and then we're going to do the mole ratio, and then we're going to change it back to a mass again. So we're going to do this now like the big kids do it, which is just in one-dimensional analysis chain. If you would rather break it down more step by step, fine with me. But there is some advantages to doing it this way that I will talk about in a second. Okay, so I'm given a number of grams. I need to find the molar mass of the thing that I'm talking about right now, which is hydrogen. I look at the periodic table. I just look at 2 hydrogens, not 4, not 3 or 6 or anything like that. The only time you use the coefficient is in this middle part right here. So it is 2.02 grams is the mass of 1 mole of hydrogen. I will say again, notice that when I'm doing the mole unit, I'm always attaching the thing that I'm talking about to the mole unit. You have to do that so that you'll, otherwise the mole ratio part will get screwed up. Okay, gram unit cancels. So the mole ratio, that's where I'm using coefficients. The coefficients in this case are 3 and 1. This, 3 and then an invisible 1 that's in front of the nitrogen. What goes up must come down. Moles hydrogen is on top. Therefore, moles hydrogen will be on the bottom in the next one. So they always alternate like that. From here, moles, whoops, that's not moles H2O, it's moles hydrogen. Moles hydrogen cancels out, which is what we want to have happen. Now I'm in the moles of my new thing, my unknown thing, which is nitrogen. I'm going to use nitrogen's mass. I'm always going to use 1 mole in these these first and last steps, it's always 1 mole. And so that should solve this problem. In terms of actually making this calculation, what I would do is punch it into my calculator all at once. Like so. So I'm ignoring the ones. It's everything on top multiplied together divided by everything on the bottom. You don't need to put the ones, of course, because that mathematically doesn't change anything. And make sure, the parentheses actually don't matter on the top, but if you're punching it into your calculator, make sure you put those parentheses on the bottom or it will give you the wrong answer. It'll multiply these two together, divided by 2.02, and then it'll take that answer times 3, which is not what you want to have happen. So if you are going to do this more in a step-by-step fashion or some different way, what you have to be careful with is rounding. Because there's 3 different calculations here. And if you're rounding too much or incorrectly, your answer will start to get pretty far off. Now, that said, there is certainly a certain variance. You know, if this was a test or something, and you said 159.5, yeah, I would certainly take that. But if we start doing some problematic rounding or we do too much rounding, then that can be a problem. So we don't want to do that. You want to make sure I would say, keep at least 3 significant figures as you go through. So I know a lot of you are not quite finished with this, but I just want to point out a couple things in case some of us are going too far down the wrong pathway. So again, the scenario with this problem is, as I said, ammonia is one of the most important chemicals produced in the world. You're the chemist in charge of the factory. Your boss says, we need to make 25 grams of NH3 today. Tell me how much hydrogen we need to order. How much hydrogen are we going to use in this process? Oh, I just realized I have the last step wrong. Now, of course, in a factory, you'd be making a lot more than 25 grams, but still, the overall idea is the same. We're going to change the grams to moles of the NH3. We're going to utilize our mole ratio here. I messed this up. And so we have grams to moles of the NH3. So then in the next step, in the middle step, the coefficient in front of NH3 is 2. The coefficient in front of hydrogen is 3. Here we go. Did have the answer correct. And so we get 4.45 grams. Now, there's definitely, depending on how your mind works and all that sort of stuff, there's people who get lost in the dimensional analysis and they could do it some other way. And like I said, when I was in high school, I wasn't a big fan of dimensional analysis. So like me from 1995, I would have started off with the 25 grams and it would have been apparent to me that I need to divide, in this case, by the mass of the thing that I'm talking about. And so that's 1 point. Now you got to be really careful with the rounding. Like if you round this to 1.5 or something like that, you're going to get an answer that's kind of too far off. So we need to keep some extra sig figs. And then I would have said to myself, well, let's see, I need to compare the NH3 to the hydrogen. That's a 3-to-2 ratio. Okay, I need more. Basically, am I going to multiply by 3/2 or 2/3? Well, 3/2 because I need more hydrogen than ammonia, so I'm going to multiply that by 3/2, and then I'm going to get like 2.20 moles of hydrogen, and then I would know, oh, it's 2.02 grams. And if that kind of thinking is, works for you and what I just said makes sense, I'm totally fine with you doing this problem this way, as long as that work, it needs to be there on tests and quizzes and so on to prove how you worked your way through the problem. So I'm fine with it either way, as long as we're not making rounding errors and things like that. Okay. Now this last one here. I do believe, though, the worse you are at math and the worse you feel like you conceptually understand this, the more you should try to do the dimensional analysis. Okay. So this question 2C says, suppose a chemist needs to produce 10 grams of NH3. So, if you're in charge of the ammonia factory, you need both of these things. It says how many grams of hydrogen and how many grams of nitrogen are required. So, here's the thing about this. There are a couple ways to do it, but what you cannot do is you cannot just try to do this like in one big step, like one big dimensional analysis chain. You can't do that. You have to pick one of these to find first. It doesn't matter which one you pick to find first. Maybe you're going to find the nitrogen first. So it's a gram-to-gram problem with nitrogen. And then from there, then you can find the hydrogen in a completely separate thing. Okay, so there is one way to do it, kind of a shortcut type way, but you can just you have to do the stoichiometry completely twice. Okay, so I'm going to have you try this. Just pick one to start. You can start by finding the hydrogen first. Just ignore the nitrogen for the moment, or vice versa. It doesn't matter. So here we have 3C, and we have the answers to 3C. And so we could have done either one of these first in either order or whatever we were going to do. And I get 8.22 and 10.78. So here I did this by doing the stoichiometry twice. Did anyone hit upon, or can you think of another way, once I got this, that I could have got 1.78 without doing all of this again? Go ahead, Caden. Subtract it from 10, yes, exactly. And the reason that works is law of conservation of mass, and there's only one product. This would not work if there was two products, but there's only one product. So because of the law of conservation of mass, these masses do have to sum to 10. So either way you do it, whichever one you get first, of course, if I do this and subtract from 10, I'm going to get this, or I can do the stoichiometry twice. It all works out. Questions about that? Okay, I want to mention a couple things about the next page. So some people get confused and tripped up when we've been doing these little bit harder problems, but it goes back to like number 3, which is actually should be an easier problem. Certainly it's less steps. This is just saying we've got 5 moles of this, and it wants to know moles of this. Okay, so this is just a one-step problem. All we got to think about is this mole ratio here, this 4-to-2 mole ratio. So we're literally just doing, like in this case, 5 moles of Na. We're only doing the mole ratio step, so 4 moles of Na for every 2 moles of Na2O. Or if you realize by looking at it that it's going to be half as many, and you just want to do 5 divided by 2, again, I'm cool with that too. So that's that. It is 2.5. 4 is also the same. I mean, it's the same type of problem. It's a little bit more complicated. So this is one of these ones where we have some trickier ratios for sure. So this is where dimensional analysis can be our friend if we're not sure how to handle these a little bit trickier ratios. People get a little confused about the wording of this one sometimes, but it's just asking you to do the mole ratio 3 times. And you do have to do it separately. So you can use the 7-to-4 mole ratio to figure out the moles of oxygen. And then you could actually take your moles of oxygen and figure out these, or you could go back to the H3. It doesn't matter. Once we have one of them, we can figure out any of the others. So it's just asking you the moles 3 times is what that's doing. Questions about that? Um, 5 is not balanced. So I said we haven't ran into this yet, but it gives you a hint there. You got to make sure you balance it or you're going to get that one wrong. 6 and 7 actually require you to write the chemical equation. But I'm going to give it to you just because I don't want that to be the reason you miss this question. So I'll help you out here. But yes, we would have to think about all the rules that we learned in the last unit to actually write this chemical equation. Obviously, if your chemical equation is wrong, you're going to get the answer wrong unless you get really lucky, which is possible. You can definitely make a couple mistakes that cancel each other out. So that's 7. 8 is another one that people get a little bit confused on sometimes. They get thrown off by the scientific notation. But one way around the scientific notation problem is we could just change it out of scientific notation. The -2 means move the decimal 2 spots to the left. And then another complaint I've heard about that problem is, hey, I don't know what propane is. Which is fine. But if we just apply a process of elimination, we know that O2 is oxygen, we know C2O is carbon dioxide, we know H2O is water. And from all that, we can realize that propane must be that.